Okay. So let me just get my marker. Where is it? So yeah, this stream we're just gonna do something we're gonna do something kind of in depth. We're gonna go into the technique of solving partial differential equations, linear partial differential equations, with the separation of variables technique. This technique shows up everywhere. Right. I'm just gonna announce. I'm just gonna make sure that people know that we don't need a Twitch account to watch. But anyway, yeah, we're gonna try solving some linear partial differential equations using the separation of variables technique. It's incredibly powerful. It shows up in solutions to electrostatic equations. The heat equation was the original one. Gravity, you can use it there. The Schrodinger equation, that's what you do 9 times out of 10. In fact, all the orbitals of an atom are expressed in terms of, or derived from this technique, separation of variables. And the technique itself, the basic idea isn't too complicated. All you really need to do is guess a form of the solution of the differential equation, as you do with every differential equation. In this case, if you have some differential equation of some function of f of x, y, you assume that you can separate this out into a function of x and a function of times a function of y, right? Now, there are some examples where you can't do that. For example, if your solution was x to the y, you couldn't really separate that out into a function of x times a function of y. Okay, moving on, I think it's best to jump right into it, and I think we could start with possibly the easiest one, the heat equation. So, to start out, I'm just going to write it and then explain everything that's in it. Okay. So what this means is the rate of change of temperature is proportional to, this is the proportionality factor, it measures kind of how easily heat diffuses through the material. And this kind of is an infinitesimal average. So if you have a heat distribution that looks like, or a temperature distribution that looks like this is your x-axis, this is your temperature, right? If you have a heat distribution that looks like this, or something like that, right? What'll tend to happen is that this guy is kind of surrounded by an average that's a different temperature than it. So it's going to try to move towards that average. So for example, this guy is going to try to move down. This guy will try to move up because its average temperature is surrounded. So temperature is proportional, is related to heat, and heat flows from hot to cold. So this is hotter than its neighbor, so it's going to flow. This point right here doesn't really experience any change in temperature because heat's flowing from hot to cold, but just kind of flowing through. There's no net heat flow. So this will kind of level out, go to more like that, and it'll keep kind of compressing until eventually it ends up being a constant heat throughout the entire thing. Now, going into this equation, I'm going to kind of introduce a little bit of a weird notation. I've normally seen that with Greek variables you use capital letters, with normal variables, you also use capital letters, but in writing it's hard to tell. So your first step would be to assume that temperature, as in this case, let's do a one-dimensional one. So one-dimensional, and let's also make it Cartesian, because Cartesian is pretty easy. So right now we're going to make this the Laplacian in one dimension. So this operator is, it kind of measures the average. You could think of it as, if you remember, del of some scalar function. So this is the gradient. This is the divergence of the gradient. Anyway, to go through a little bit of Calc 3 review. Del, you can express del as a vector, at least in Cartesian coordinates. Yeah, like that. And so if you apply this to t, well, this is the basis vector in the x direction, this is the basis vector in the y direction, this is the basis vector in the z direction. If you were to describe a vector like with parentheses, it would look something like this. So this is the x coordinate of this vector is going to be this, the x coordinate is going to be this, and the y coordinate is going to be this, and the z coordinate is going to be this. Alright. Let's see. Just going to check, see if anything is happening. Oh, that's good. Anyway. So when you dot this into itself in sometimes you write this upside down, so you could do it like this, and it's coordinate independent, so you can write in any coordinate system, and we'll do that later. But for now, we're just going to do Cartesian because it's nice and simple. So do this guy. We take the dot product of this with itself, which is x coordinate times. It's not exactly times, but it's similar enough. So this applied to this, or times, or whatever, would be this plus this times this, or applied to. You could make it times if you were treating these as linear operators and kind of like matrix multiplication, but anyway, it wouldn't be. This is the Laplacian in 3 dimensions in Cartesian coordinates. So now, I told you earlier that there was like a one-dimensional version of the Laplacian, and what that means is that these two coordinates don't matter. So they don't contribute anything. If you want an example, maybe you could do like a bar where the two examples are kind of weird. One is just a bar like this. It's actually a really bad example because so one example is kind of like a bar where it's thin enough that you don't care about how temperature is flowing in this direction and this direction. You really just kind of want the average temperature at a point. If anyone's watching, seeing anything weird going on with the stream, I apparently have encoding overloaded, but it doesn't seem to be a problem, I think. Anyway, if you have a bar where it's thin enough that the temperature doesn't matter and you're only looking at the x direction, or the temperature differential across from like the bottom of the bar to the top of the bar, doesn't matter, you can make it one-dimensional. The other case is kind of weird. It's pretty much the exact opposite. So if you wanted one where the x dimension matters, it's either the two cases basically either it's so small in this dimension that you don't care up and down, or it's actually infinite in this direction. So like, say this is the x direction, we could do do it like this, right? In this case, the y and z don't matter because there's not really much going on there. Y, z's out of the board. In this case, the y and z don't really matter because it's infinite. It's kind of symmetric. So if you just calculate in one dimension, the x dimension, you end up getting it in this dimension, and also it's hard to draw, but this kind of bar structure here, it goes off infinite in that dimension. So in this case, the only thing that could really change is your x position because it's just so big that the actual heat doesn't go through it in any meaningful way. As an example, we'll actually use this approximation to calculate, say, what it'd be like for a star going through a galaxy, what it would be like to heat up like a flat steak, because while it will affect it, you want the temperature in the middle to be good, so the heat flowing in from the sides isn't comparable to the heat flowing up and down, and it's so spread out that you could probably get away with just one-dimensional version. Anyway, so the one-dimensional version basically just means that whatever you're taking the function of, right? So if we wanted, say, del squared f of x, y, z, we would get d squared f x squared plus d squared f y squared plus d. Keep saying squared, it's technically not squared. So we'd end up getting this. But if f doesn't depend on y or z, right, then these are both 0. So if we do instead of this, so say f just as f, we could model as f of x, it doesn't depend on y or z, we just end up with squared. Alright, a little bit long-winded, but that's kind of the general idea. If you wanted a higher dimensional one, you could technically extend this to any number of dimensions. You basically just keep adding terms here. And moving on, we're going to go back to this equation up top. Alright, so there's also, I'll just mention this because there is. You can also add, say, a source term somewhere in there that depends on position and time. So, for example, if I had, let's say like a 2D grid or something, right? And I was adding heat here, but like it was oscillating with respect to time, so it was like this point would get, or this kind of area would get a lot of heat. But the amount of heat I was adding was changing over time, then I would just add a source term in there. Anyway, moving on a bit. So now, what we're going to want to do is convert this to the one dimension. First off, we're going to drop the source term because it's just annoying. You can have it if you want, but we won't need it. So the first, let's just focus on a specific problem. Let's say that I have a bar. This is the class A example. A bar that is 2 meters long. So let's try here's over here. And we're going to do two different kind of scenarios. The first, we're going to heat up. There are two different kinds of boundary conditions. One of them is that we're just not going to add heat to the thing. So we're just going to keep heat from flowing in or out. And we can do that by saying that at the endpoints, the change in temperature is 0. So there's no, or the change with respect to position is 0. So there's no heat flowing this way and there's no heat flowing that way. I think it'd be better to go to an example. So So let's focus on the first one. That's probably less confusing. The first one, we just fix the temperature at both ends. So if we have, say, like a bar of some given initial temperature distribution, we put one end in basically like an ice bath, and the other end we put on a burner or something, right? How does that affect the heat? Well, since the burner can output a constant amount of energy and can really ensure that this is a constant temperature, this down the ice bath could ensure that the bottom of the bar is a constant temperature. What that means is that the temperature at the 2 points is going to be fixed. It's not going to change. It's not going to increase or decrease. So yeah, we're gonna do that one first, and we do that by imposing what are known as boundary conditions. These are pretty simple. So the first one is we're going to say that the temperature at x equals 0 for all time is equal to, let's just pick a number, say 273 Kelvin. So this is the freezing temperature of water, or the temperature of water freezes. That means 273.15, but whatever. And yeah, actually, let's say the temperature at the other end of the bar, so 2 meters. Yeah, I'm adding units in here because eventually it'll kind of get weird getting it back to reality, but you can always, since we'll be messing around with these things, it'll kind of work out. So the temperature at the other end of the bar, like 2 meters, we're also going to hold that at 273 Kelvin. And I think we're going to start with a simple thing. So now we specify how it works at the endpoints. These are boundary conditions. And now we just need to specify an initial distribution of temperature. So let's say for some reason we had a bar and we heated up the center, for example. So in this case, the temperature distribution might look something like this, right? So the question becomes, how do we model that? Well, we pretty much just say the temperature for throughout the bar, so we leave x to be whatever, right? For at time t equals 0 is equal to some function. In this case, I'm just going to say we heat up the bar uniformly, so it's a constant temperature. So it's constant temperature of, say, 300 Kelvin, right? If I want some kind of variance, I could do like 300 Kelvin times the negative x. X over L. That's not legible. X over L minus half squared or something like that. That would be a bell curve with the highest point in the center. So this is just some function. It doesn't matter what it is. Anyway, well, for the things we're doing, it technically does matter. It has to be L squared integrable, but if you don't have an L squared function, I mean, what are you doing with your life? But I don't think is that possible? I don't think it's actually possible in like the physical world to not have one. So anyway, we're just gonna say it's a nice constant 300 Kelvin. Okay, so this is closer to room temperature. This is like a little bit above room temperature. Anyway, so now that we have these, we're gonna rewrite this so we just take into account squared t over dx squared. So remember, we're only doing one dimension, so we don't need all three of these. Equals dt. Right? Yeah, and I'll rewrite that. It could be big. Yeah. I just realized it's kind of a, how do I put it, blessing and a curse to be live stream, because live, people can respond and like ask questions and stuff. But also, if you jump in the middle of it, you're kind of screwed. So. Anyway. It should be dx squared. There we go. Okay, so now we've got the boundary conditions. We should kind of come over here. Yeah. Hoping I can move to the right so I don't keep going off screen. Yeah, and let's just say alpha is 1. This has units of, this under here has units of 1 over meters, or 1 over length squared. The del squared has 1 over, the Laplacian has units of 1 over length squared. Temperature has units of temperature. So what we want is alpha to be, alpha times this equals 1 over t, or 1 over second. So alpha meters squared equals 1 over second. So alpha has units of meters squared over second. And that makes sense. So I think I'm just gonna do something pretty standard, like 10 to the negative 6 meters squared per second. I think that's in the ballpark for water or something like that. I'm not too sure, but it sounds like it could probably work. Anyway, moving on. We've got all the numbers we need to actually go into this. So let's start it up. So the first thing we do is, for separation of variables, after 30 minutes of watching, and probably closer to 20, we can now actually get into what separation of variables would look like. In this case, it's really simple. All we do is we just say, let's assume temperature, which is a function of position in time, is instead a function of, or the product of two functions. And I'm going to do kind of a weird notation. Normally I would just use capital letters if I were typing this out, but because it's hard to tell a capital letter from a lowercase letter, I normally just kind of add serifs to all my variables. So anyway. Or I might even use a different symbol. I think I'll do that for temperature at least. So yeah, I'll use a theta, which is kind of like a Greek T, but we'll use capital theta. Anyway. So that's my idea. Now, using this, we're going to plug this expression into here. And so what we get is alpha e squared x squared x theta t t. Oh no, I've gone too far. Anyway, I'll just rewrite it. I'm not in a rush. Now I'm just imagining someone like, oh my god, I have a bar of temperature 300 and like put in initial conditions with 273 Kelvin at both ends. And I have them with this, and like they just have all these variables, and they need to solve it, or otherwise the building's gonna explode. Anyway, weird thought of the day, or like weird thought of the hour. That was pretty generous. Okay. Now we've written this out. Notice something. This guy over here, this is the second derivative of this with respect to x, right? So this is a product, so we can expand it out. I'm going to do it over here, just so you can see the general principle, and I'm going to do this one first. Is that even visible? So let's just take the derivative of this guy with respect to. Anyway, so product by product rule, we end up with gross. Keep writing in the center because I don't think I'm going to write on the next line, but I don't. So derivative temperature with respect to time is equal to this guy up here, which by the product rule is dx dt times theta t plus x theta t. Okay, but notice something real quick. This guy right here is actually not a function of t at all. It doesn't depend on t. So the derivative of this with respect to t is 0. So this whole term goes away. And we're left with x. Okay, so now if you look at this above, it's kind of like this is a constant with respect to this, so you can pull it out front. And we're going to do that with both of these. As you can imagine, the same thing happens if you take higher order derivatives. So second derivative doesn't actually do anything different. So we're just going to pull that one out. So we're left with alpha theta t squared. That was, I don't even know I tried that one. That was just a failure. Gross. X squared equals x theta t. Okay, so now here's kind of the that was the first thing we did. We just assume it's of this form, right? And then next thing we did, we just kind of broke apart all the constant stuff, so we didn't need it. So next thing we do is pretty simple. We divide both sides by whatever t is. In this case, it's this. So we divide by x, big X times theta, which ends up gives us alpha 1 over x. And just for, I think it'll make our math a little easier. It doesn't change anything really, but I'm also going to divide by alpha. T. We're going to throw a little alpha. Alpha should be. I'm annoyed. I wrote that one really well. I wonder how loud I am. I should be pretty easy to hear, even with my back turned. I mean, this is a solid wall. Sound bounces right off of it. Theta t Okay, now we got this. I want you to consider something. Say we evaluate temperature at the point, say 1 meter, and we evaluate at time t equals 2 seconds, right? Okay, so whatever we get for this side, so we take the derivative of this twice, then evaluate this. So we're going to look at evaluating this side. Well, this side doesn't depend on any of the time, so it's going to give us, we just plug a meter into all this stuff after we take the derivatives. Same with this side doesn't depend on position, so we take the derivative, we plug in time, calculate that, and everything's all good, right? So let's just say for the sake of argument that that we plug this in and we get, say, k squared for some reason. Will become apparent later why I did k squared. So, we can keep it simple. Say we're gonna plug this in 1 meter, 2 seconds, and we plug it into the left side and we plug in the right side, right? So in doing so, let's say we get just some number a, and we doing it over here, we get some number b, right? So we end up getting that. Now, let's consider what happens if I change this from 2 seconds to 3 seconds. Okay? So now I plug 1 meter into here, I get the same exact result. I plug 3 seconds in here, and maybe I get something. So I get A. I plug 3 seconds into here, and so I get something else, C, but because A equals B and A equals C, B equals C, right? So no matter what time I plug in, this is going to have the same value because this side doesn't change, right? Likewise, the same thing could apply for this. So if instead I plug in 2 meters, 3 seconds, right? Well, this is still going to be C, but maybe this is D. C. So, but now all these numbers are equal. So all of these are equal to the same thing, and it doesn't change with respect to time. It doesn't change with respect to position, so it has to be a constant. So now, here's where things get actually interesting, because up to this point, we just kind of done a little bit of setup. We haven't really gotten to the punchline of the separation of variables technique. So now, let's try that. So we say this is equal to some constant, and I'm going to pick k squared. Just make sure I get everything right, because sometimes because if you get the sign wrong here, it could mess with you later, but it just turns into like an imaginary thing. So it doesn't matter what constant you put in here. You put in a k squared because later on you'll have to take the square root of it. And I think you put in, yeah, I think we're going to do a negative k squared. And that's just because if you end up solving this differential equation, you need something that satisfies these boundary conditions. So to do that, you need to pretty much plug this. So we can treat these as two separate equations. Well, it's negative k squared. And we also have I don't think I'm boxing through everything. I think we can at least that's just kind of set up. So now, I'm going to erase this because this is just product rule. Anyway, so let's split this in half. I'm going to solve this half over here, and I'm going to solve this half over there. So some of you guys might be that everything to the right of that was just wrong. I did that, but right. So now you guys might be a little worried because I've said it's equal to some constant, right? But we don't actually know the constant. It's just kind of up in the air, and maybe we could like calculate, but we'd have to solve it, and then it ends up in a mess. But what'll save us are our boundary conditions. These guys will. We can use these to. Sorry. Exploit to figure out what this constant is, because when we actually calculate the constants for this differential equation and the constants for this differential equation, the coefficients, what we end up doing is we have to basically clean up everything. We'll get like the function of the constant. We need to be in a certain place for every single one. So anyway, moving on. This one isn't too hard. If we multiply both sides by this, we end up with theta t equals negative alpha k squared. Theta, I'm going to rewrite that one because I think it's good. T. Okay, so we got this boy. This becomes a pretty standard differential equation. I don't want to go too in detail, but basically, as with every differential equation, you guess a form of the solution. In this case, you could guess like polynomials, e to some function x, but in this case, guessing e to the rx, right? So if I'll do it over here. For this one, you just guess e to the rx. R happens to be this guy. So what we end up getting is that theta t is equal to some constant e to the negative ak squared t. Now, this constant will, because this is, remember, t is a product of these two functions, so whatever constant this is, we'll actually get kind of multiplied by whatever constants we get over here. So I'm actually just going to erase it. We're just going to look at this. We'll add back the constants later and I'll clean up everything. So here I'm actually going to do the full thing. Multiply both sides by x over x, negative k squared, that, and then add that to both sides. So we get d squared, so dx squared plus k squared x 0. If we guess e to the rx for us, where r is just some constant, we plug this into here, we get r squared rx plus k squared x equals 0. We can divide by e to the rx since it's never 0. So we have r squared plus k squared equals 0. So r equals plus or minus ik. Right. So our solution is and this is a linear differential equation. So if you plug in for any linear differential equation, if f of x and g of x solve then any linear combination can solve it. And linear combination means that any constant times the function times the first function plus any constant times the second function. So in this case, the full solution, we plug in this e to the rx works if r is plus or minus ik. I is the imaginary number. So x function of x equals constant 1 I kx plus constant 2 e to the negative I. Without going into, I don't want to go too in depth in here, but it turns out you can actually rewrite this as a combination of sines and cosines. So this ends up becoming C1 cosine kx plus C I sine kx plus C2 cosine minus sine. And this is known as Euler's formula. Anyway, going from here to here, you use Euler's formula, and then if you plug in certain values for these, you can right. So you can convert it to this. It's not too difficult for time's sake. I also should have done that one over there because that has way more space. I don't know what I was thinking. But I'll just summarize. You can rewrite this in terms of sines and cosines and make it all real. Right. Anyway, so I'm going to stick with this. And I use C for constant normally, but in Fourier you kind of use. You tend to use A's and B's for some reason. I'll make them lowercase. A cosine kx sine. Okay. So now, if we multiply this times this, we get a solution. We can plug it in, it gets all the right answers. The only problem is we don't really know what case. So now, we're going to need to evaluate the boundary conditions. So real quick, I'm just going to write, and you can get different things if you plug in different K's. So for now, I'm just going to make a note over here. Temperature, function of x and time is equal to e to the negative alpha squared kt. Times a cosine b sine. Yeah. I'm actually going to denote this with the subscript k, just for completeness sake. So anyway, because this any value of k that you plug in will actually solve this differential equation. So any value of k will solve it. But actually, once you apply the boundary conditions, then none of this ends up. Then this stuff goes away. So in this case, we're going to apply our kind of first two boundary conditions. These two together are what we'll really end up using. Oh yeah, I just remember that you can, since these are taking derivatives, you can add an arbitrary constant. Anyway, so now we're going to need we're going to need to find out which one of these work. Gotta think for a second. Because as a short answer, this will end up being something like pi over L or 2 pi over L, and this cosine term goes away and stuff like that. Oh, I remember. So, yeah, so we do t k as at 0 t equals e to the negative alpha squared kt times, we plug in 0 for x, this whole sine term goes away and leaves us just the cosine. We end up with a cosine ax, but this becomes a. This just becomes a. Right? Because cosine of 0 is 1. Oh man, I just realized I have a and alpha. I'll make these uppercase, just so it's really clear what's going on. Doesn't matter. So now, this guy just becomes this part times a, right? And now if we plug in L, so let's plug in T, LT equals, you still get the e and the negative alpha t thing sticking around. Oh, and this has to equal 273 Kelvin. KT. And now when we plug in L, we end up getting a cosine KL plus b sine KL is 27. Okay. It has to be constant for all time. So actually, this is kind of a fun one. It has to be constant for all. It has to be 273 for all time. So what that means is that basically one of these terms has to go to. This term is going to cause a problem because whatever you set a to be, this is actually going to mess it up. It's the initial distribution, no determinants. Plug in 0. Oh, I remember. I skipped a step. And that's a little bit of a problem. So yeah, actually, this is gross. So I tried doing it with just one, but remember, this is a linear partial differential equation. So really, this solution is only like one possible part of the solution. So now we need to do this. Our total temperature as a function of x and time is equal to some kind of sum, any linear sum over all the k values of some over the tks. T times the right. This has a constant in there. This has the two constants in there, so it's already kind of taken care of. But I needed to express it like this. So now we can actually get working on this. So if we plug in T okay. So now just making sure everything checks out. Because as a bit of a spoiler, this is just going to turn to just the signs, and k is going to be once again pi over L. So yeah, I forgot the step. So we found one possible solution, but since it's since it's a linear differential equation, every single linear combination of these is a solution. And so I've already kind of added the constants here. So if I multiply these by constant, it doesn't do anything. It just goes. It gets absorbed in the a and the b. So like, if I made the constant like 2 for something, I could just make a and b both twice what they are. So now we can move forward. Okay. Use a function of 0 temperature. This ends up becoming some. I'm just gonna leave. I'll leave the k. We plug in 0. This becomes sum of all the a's times e to the negative alpha at alpha squared t to equal to 7. Right, because you plug in 0 for this guy, you plug in 0 for this guy, and this whole thing doesn't work. So now here's where the first kind of problem comes in. If I try to plug in, yeah, okay. Because what we're going to do is, this is basically a constant term. As you see that this guy takes derivatives, so you can add any constant term to it and it won't matter. So we're going to kind of pull out the constant term and kind of see what's going on there. Okay, so let's for a moment just look at like what happens if we just pick a k equal to 2, right? Just because there's no particular reason. I'm just picking a number. And let's say that that's our only k. So let's just kind of, this is like hypothetically. I'm actually going to even box this off because I don't want you mixing up with it. So let's consider a hypothetical. Let's just say that t as a function of x t is equal to ae. Let's just plug this in because it's not that big. T as a function of this is literally just these need to be function. Sorry about that. ak e to the negative alpha squared 2 t, and there are units in there that I'm ignoring for now. And we set that equal to 273 Kelvin, right? So the problem is we need this to actually work for all values of t, right? Because this is arbitrary. But if I plug in, this is clearly an exponential function. So if I try to do, say, this is a2. If I try to plug in, say, let's say that, what was it, alpha is 10 to the negative 6, so we'll go ahead and do that. Yeah, so if we plug in, so t00, right? Sorry, I'm kind of jumping around. t00 is just a2, which equals 273 Kelvin. Right, nothing weird about that. But now, the problem comes in once we add this exponential term back. So in this case, we have t00. I'm sorry, this shouldn't be a squared. This should be 2 squared. I don't know. How long have I made that mistake? That's gross. Ugh. Real sorry about that one. Anyway, so this is e to the negative alpha 2 squared t, right? So now we're going to, so a2 has to be this because I plug in 0 for this. But if we calculate, say, t01, right, this becomes 273 Kelvin times e to the negative 10 to the negative 6 meters squared per second. This is a very long-winded way of saying that this just k is going to be need to be plug in 1 second, and then alpha k squared. Oh, k would be in units of 1 over meter, so to speak. So negative 2 seconds. So all the units cancel out. If we plug this in, then we end up getting basically 0. We end up getting a totally different number. This is going to change over time. The only way that this doesn't change over time is if k equals 0. So if we have a k equals 0 term, that's really the only way to maintain that. So first off, t0t has to equal roommate just came in. We plug this in. We pretty much have to do a few things. First off, we need a k to be 0, right? So I'm just going to pull that out. A0 plus sum of the negative alpha squared times AK. Remember, this A is basically the cosine coefficient. Alpha squared. Oh my god, am I gonna keep doing that? Squared T. Right. It's 273 Kelvin. Okay, so now if we plug in T equals 0, we can see that A0 has to be 273 Kelvin. So put K not equal 0. So in this case, this implies that A0 equals 273 Kelvin. Cool. So now we're going to move to this guy. We're going to kind of cancel these out because they're there. So we end up with the sum of all the AKs, k not equal to 0, of e to the negative alpha k squared t, right, has to equal 0. And there's simply no way to do it for every arbitrary time, because all the exponentials will end up working with that, unless all the AKs are 0. So that implies that AK not equal to 0 is equal to 0, right? So now I'm going to readjust. I'm going to rewrite this in a more meaningful terms. So the first boundary condition basically showed that there are no cosine terms. There's one constant term out front, and that constant term just happens to be when k equals 0. Okay. So I'm actually going to rewrite this, pull this out. I'm going to try to keep in symbols as long as I can, or variables as long as I can. So this becomes A0 plus sum k not equal to 0. Actually, it doesn't matter because all the cosine terms are blank. So this becomes B sine kx e to the negative alpha squared t. Alright. So yeah, we basically just got rid of all the cosine terms. Pretty simple there, if you don't make multiple mistakes like I did. But we're done with that. So now, we got our first boundary condition done. We're going to move on to this one. So T LT equals sum over K E sine K L. So we're going to call this A0 plus sum K. Okay. Sine Kx. And this is now L. Okay, and this has to equal 273 Kelvin. But hold on, if we cancel out these guys, right? Remember, this A0 is equal to 273 Kelvin from earlier. In fact, I might even write that down. Actually, I'm not. I'm just gonna write this 273. I apologize for the big K's and little K's. It's kind of a mess. But yeah, so 273 Kelvin. Okay, so cancel these guys out, and we're left with kind of a similar situation. Sum K BK sine KL negative alpha squared t equals 0. Okay, so now there are two ways out of this. First, we could do what we did with the cosines and make all the bk 0, in which case our function would be 273. Just straight up 273 Kelvin. So the problem is this starts out as a different temperature. So if our temperature for Tx0 was just 273 Kelvin, then nothing would change. It would just stay at a constant 273 Kelvin. So we can't make the bk's equal to 0. So now the other way to make it equal to 0 is to make the sine term equal to 0, right? And to do that, we need that to make all the signs 0. So now, just box this off. Sine KL equals 0 implies that KL equals n pi, where n is in integers, right? And then if we divide, we get k equals n pi over L, where n is some integer, right? This fact down here comes from the fact that sine, and draw your unit circle, you start at 0, you're there, that's n equals 0. You go around this way, 1 pi over L. The over L is to scale it, so, because you multiply by L every time. You go around here, pi, or this part. You go around pi, you end up here, we're still 0. Go up here, you get pi, another pi, you're 0. You go the other way, you get 0, so it's 0. So now, there we go. Going back, we can actually rewrite this equation totally in terms of we can finally plug in the k. So we end up getting the constant on the boundary conditions. This is pretty standard. You notice that it actually depended on the length of the bar, as you might expect. So really, I'm going to rewrite this. I'm going to rewrite this as a sum, and I'm going to do two things real quick. Equals 1 to infinity. I'm going to reindex in terms of n. N pi x over L e to the negative alpha pi over L squared t. Right? So you plug in the k's, and you'll notice that I said n could be any integer. Is that? Hold on. I might make this a little better. And I'm gonna check DMs just to make sure someone didn't message me about something, because I view my not Twitch. Anyway, so you get this guy here, right? You've got the boundary conditions, and you've satisfied these two. Okay, moving on. Sorry that was a little bit longer than I expected. I'm a little rusty with this, but who knows. Anyway, so now we just need to plug in our last boundary condition. This one's going to be kind of weird. Tx0 equals 273 Kelvin plus sum of 1 En sine n pi x over L. And this equals 300 Kelvin. We can subtract the 273 from both sides to get 27 Kelvin. Okay, so now we kind of have a weird scenario. We have a bunch of signs added up together equaling a constant. Hold on, lighting's gonna change in a second. Sorry. Okay, it didn't change that much, which is good. I kind of have some stuff blocking. By the way, so we should get 27 because we subtracted that from that. All good. But now we kind of get all these signs added together, multiplied by some different coefficients, have to add up together to equal 27, right? So the question becomes, is there any way to represent 27, a constant function? So this function would look like this. It would actually look like this. So here, but remember, if you plug in L, this part goes to 0, right? Because it's sine and pi. So our function looks like this. And this is temperature. This is at least at time t equals 0. So now the question is, what is this kind of, is there any way to represent this as signs? And yes, you can imagine it. So if we do a sine here, maybe go a little bit above, that's pretty good. Then we could do, say, a sine with, this one's a little too low, this one's a little too high, this one's a little too low. So we could do another sine function, like with 3 times the period, and I'm kind of messing around here, this should be way lower. And as you can imagine, this adds some more here, takes some from here, and so on and so forth. Anyway, this is kind of what Fourier analysis is. So now we really need some way of breaking up this kind of function into break up this into a bunch of sine and cosines. And we're going to use kind of an idea from linear algebra, the idea of orthogonality. So if I kind of jumping to a different idea for a second, say I have some vector in space. I'm just going to call it right, and it doesn't really matter which direction it points, but I want to change its basis to something different. So maybe it points up and down, maybe it points left and right, maybe it points whatever. So I want to rotate the axes. So the question is, how can I get from one basis to another? And the real way to do it is you get a bunch of orthonormal vectors, right? And you take the dot product of that with the orthonormal vectors. So sum in, yeah. And in a similar manner, we're going to do something similar with a property of this integral. Notably, that if we take the integral from 0 to L, or maybe it's L to negative L. Sorry, just think for a second. Yeah, might be good to actually just look this up real quick. Because once again, I never memorize a lot of these formulas, but yeah, and there were like 15 different ways to write a Fourier series or Fourier coefficients and stuff like that. It's kind of nasty, and I really don't like it, but especially since some of them are kind of engineering style ways of doing it, and I just don't. Yeah, it'll work for any length, and it's 2 pi. Let's see. Close up. Fourier series. I was looking for the right form. I think I have it. Yeah, there we go. So the main idea is that if you integrate over any period of 2 pi sine mx sine nx dx, right? This is equal to this is equal to pi if m equals n, and it's equal to 0, m does not equal. There are similar identities for cosines. For example, if we do the same thing for cosine, we'll do the sine one first, the sine cosine one. This is easy. And x, it just equals 0. And then one more, we have negative pi to pi. And it doesn't matter, you could add any constant to these and you can still get something worthwhile. Cosine mx times cosine nx, you end up getting unit being 3 possibilities. 2 pi n delta. Yeah. 2 pi if n equals m equals 0. You get pi n equals m but does not equal, and then you get 0 for n does not equal. So these are kind of just general rules here, and we can use that to our advantage. In this case, where these are integers, so m and n have to be integers. In this case, you can make a couple of trig substitutions in here and pull it out. In this case, we want to do, if we let u equal pi over, if we let x equal pi times u over L, right? Then, yeah, so I'm going to focus on this one because we're just dealing with signs right now. So now we're going to make the u substitution equals L over pi x. And the idea is I want to get this into here, right? But I'm kind of a little iffy on it because that's, so if I plug in x equals pi over L times another variable, which I have to, I'm getting this, so du equals L over pi dx. So plugging that in, this becomes L over pi integral from negative L to L. Let's see. Make sure I'm doing everything. Pi over L. Whoops. Pi over L d. Sorry, it's kind of a weird substitution. Okay, moving back. So now you just make this substitution. This becomes sine m pi x over L times sine n pi x over L dx. Hold on, should it actually be L over pi? Am I making a stupid mistake here? First off, these should definitely be used. Okay. And since I made a u substitution, this doesn't change the value of any of this equation. So if I divide both sides, yeah. So I'm going to do, this is still equal to that. But now if I divide, I'm going to erase these two since we're not using them at all. Great, so now I divide both sides by pi, so I get 1 over L, I go from negative L to L, sine m pi. No, I'm just gonna plug x back in since I'm just renaming variables. There's nothing really too crazy there. N pi x over L x equals pi when m equals n, but I've divided out the pi, so this just equals 1 m equals n and 0 m does not equal. And if you want, you can prove any of these using product to sum, or You could rewrite this in terms of complex exponentials, but this is sufficient for now. So now what we have is kind of like a little, each of these is kind of acting like a little basis vector, right? This whole integral is kind of acting like a dot product. If you take in quantum, it'll make more sense, but your idea is basically this returns 1 for anything like that. So now, let's say that I'm gonna rewrite this over. This is some good stuff. I'm gonna erase a lot of this. Yeah, I can actually erase all this up here. Now that I think about it, I'll leave that since it's our original equation. But yeah, so let's move this up here because this is a really important fact. L. Integral from L to negative L. Sine x over L. Sine n pi x over x equals I'm gonna use this symbol. This means that this and this are equivalent. So this is pretty useful. You can do the same things for the sines or for the cosine terms. It gets a little weirder because you have to add something in. But for now, let's write that. And let's assume for a moment that our function can be written in terms of sines and cosines, right? And we don't know what these coefficients are. So in this case, we have 27k equals b times that. So now what we're going to do is we're going to multiply both sides by, well, I can erase this and do it down here. Now that I think about it, because I've already written enough there, I don't need everything else. So now we're going to multiply both sides by sine m pi x over L. So we get 27 Kelvin times sine m pi x over L, right, equals and I'm glossing over a few details, like technically these need square and Coulomb, but once again, I already have that. Bn sine n pi x over L sine m x over L. So real quick, this is a constant with respect to this, so you could pull it out of the sum. I just put it in there, and you have to do some very technical rules to be able to switch it. But now, all we're going to do is we're just going to integrate negative L to L 27k sine x over L. And m and n have to be integers, so I'll just write that. So I'm just thinking about specific things about this, but yeah. So this technically isn't just 27 Kelvin. It has to be 27 Kelvin for x between 0 and L. So this is actually inaccurate. I should have specified this before, but x is between 0 and L. I don't really care what happens at the endpoints. It's not. It has to be this. Okay, so now here's kind of the fun part. What do we do with this? Because what we have is basically graph out the temperature, initial temperature. We have something like here, and then it has to drop down at 273 here for L. So I'll actually rewrite it like this. So yeah, this is 300k, this is 273k. right? Okay, so, oh, sorry. Actually, I made a mistake. This should be 27k. There we go. So let's do this. 27k. Start here. Go down at L. Okay, so now we don't really have a definition for what's going on over here. We can make this anything we wanted, and I'm gonna have to redraw it again because this interval isn't over the right direction. We could, if we wanted to, shift it over a bit because it has to be here. So anyway, I'll draw this. Okay, this is 27 Kelvin. This goes here. Bam, drops down at L, or 2 meters, right? So now, what could we really do with this to make it work? So in this case, we don't really care what goes on outside of this region, right? We only care about what's in this region. So we can make this do whatever we wanted. So in this, but we need something over here. In this case, I'm going to apparently draw this one again because I keep adding stuff, but it keeps changing, and it's annoying. Yeah. This is gonna be a little bit of a practice thing. I'm probably gonna end up having to redo it. I keep thinking I don't need the whole thing. Or I'll probably try redoing the video. But this is L. 27k. L is here, right? And then it drops down to here. Okay, so now, what do we wanna do with this function? But we don't care about what happens basically from here and here. So why don't we just try doing this, where we know it's gonna be sine wave like. So let's make it just kind of something like this. So this is negative 27k. If we wanted to, we could probably mess around and make this like flat here, but then we'd have to add a constant, and it just turns into a mess. I really just want to get the sine function going. So what I'm actually going to do is I'm going to real quick split this integral up into 2 parts. L0. And I'm going to make this negative. Or, I'll go with this. So this is plus, but this is negative 27k. So you can technically imagine it's periodic, it keeps repeating, but once again, we only care about this area. So we're going to make our sine function like this. So sine m pi x over L, right? X plus. This has to equal, well, this is where it gets iffy. Once again, when can you change the sum, interchange the sum and the integral? So technically you would do this, negative L to L, sum infinity and equals 1, blah, blah, blah. But in this case, we're just going to switch the sum and integral, which we can do in this case because it's nice. Specifically, I think it has to be a square integrable function or something specific like that. I don't care. Anyway, and we can also pull the constant out, so we'll just pull the b. We're left with sine n pi x over L, sine m pi x over L. Okay, so now, once again, if we look up here, this basically becomes 1 if these two are the same, and it becomes 0 everywhere else. So what this means is if n doesn't equal m, then this is 0. And so the only term that really survives is bm. So this becomes m. This integral goes away. Once again, it goes to 1 or 0. Right? And this is why I was saying it was kind of like a dot product. Because technically it is an inner product in this sense. But you take the dot product between this and a basis vector. In this case, a basis vector would be something like sine m pi x over L. Take the dot product, boom. So now we just need to do this integral. This is going to be integral of this is negative cosine, so I'm going to pull the 27k out front. And then yeah, I could just do it. So this becomes negative cosine by x over L, L0 minus cosine by x over. Yeah, if we were a bit smarter, we could have noticed that this sine function times whatever our function is an even function. It's not that's so L0. Yeah, and what this turns into is 27k times, you plug in L, you end up getting m pi, negative m pi, which is pi, you plug in 0, you just get 1, and it's minus 1, so this is 1 plus that. And then this is the same as that. This is the exact same as this. Except it's switched negative. This will also end up turning out to be negative cosine. So I'm just gonna multiply everything by 2 up front. So I guess I'll make this 54. So this is 54 Kelvin. This guy right here. And these are actually all our BM terms. Real quick, just legibility check. I could write a bit. So now there's kind of an interesting trick we can do. If we look at like a cosine function, right, at m pi where m is an integer, draw a unit circle. If m equals 0, it's 1. If m equals 2, it's 0, right? Or I'm sorry, if m equals 1, then that's cosine pi, which is negative 1, so it goes over here. If m equals 2, it goes back to 1. If m equals 3, it goes to negative 1. So it alternates between 1 and negative 1. So this ends up becoming 54 Kelvin times, in this case, negative cosine. So if we plug in 0 first for m, right, then this becomes negative cosine pi. So I'll write this as 1 minus negative 2. Right. Just checking here. So I plug in 0. I should get 0 for this whole thing. Plug in 0. Yes. Anyway. So now our BM, and we can substitute n for m. So our full solution to this differential equation is going to keep this here, but I need somewhere to write it. I'll write it here. So it turns out our full solution to the differential equation is dx t equals sum, or we do 273 Kelvin plus sum n equals 1. Care about the 0 terms. Let's bring the constant out. 54 kelvins times. I'll make this more clear that it's a 4. I'll try anyway. Infinite n equals 1. Pull that out. We just get 1 minus negative 1 n times sine n pi x over L. Do I have to go on the next line? That'd be gross. Yeah, I think I do. I think I might have to erase some of this down here. I'll leave that up because the only thing I have to add is the exponential, but anyway. This is a little bit of a journey, but what are the other? Anyway, take this guy. I'm just gonna make sure I'm not doing anything stupid. Because if I was invisible for this whole thing, I just that would hurt. No, I'm good. Anyway, I'm glad you can't hear my computer fans. They're spinning. So yeah, I'm just gonna read. So T equals 273 Kelvin plus 54 Kelvin times. So, hold on. Does that actually work? That would suck if all my work was just. Yeah. I'm kind of weird out because I didn't actually set up any specific problems for this. Does this even work? I might, because normally what you get is you get some function of n. So it's not just this. It's like you add a bit of an n. And I think, yeah, I think I forgot to add it earlier, which is gross. But another form of solution. So dxt 273k plus some infinite n equals 1 dn sine n pi x over L. We take the integral of both sides with respect to sine and t, so we end up with 27. Okay. Yeah, I think I forgot L over n pi when doing the integral. That would explain it. So I'm just gonna add it here. That'll show up later. But or like an n pi or something. Yeah, there'd be no L over it. Anyway. So 27k integral to, sorry. Remember, we multiplied by 2 earlier. Sine n pi L x equals m. Multiply both sides, we get the integral. And then we also have to divide by L. That was the other thing that's missing. So yeah. Ugh, I'm being really messy today. It's gross. Anyway, 2 over L times 54 over 4 Kelvin. Gross. Times cos L over m pi. There we go. We're gonna native sign here. Cosine x over. Anyway, so we plug in 0. These L's cancel out. 54 Kelvin. I just realized probably in front of the screen. 54 Kelvin over m pi times, we plug in 0, we get 1. So plug in L, we get m pi, which is, so once again we end up with 1 minus. Yeah, I think that one should make more sense. Factor that out, that's negative. So, yeah. And this equals. Okay. Okay, so that should be correct, as far as I can tell. So yeah. Yeah, I'm just gonna copy it down. Here. Right now, that stupid. 27. 2. N times x over L to the negative alpha pi over L squared t. That should be it. If we plug in real quick, I'm gonna do a quick check just to make sure that if I plug in something simple, this. Might be really. Yeah, that makes sense. Alternate sign. I think this might be. Yeah, I'm thinking of the square wave. I just need to make sure the coefficients are correct. Yeah, so 4 over pi. Okay, and these are odd numbers. Yeah, this is it. Alright, and so this is the solution to our differential equation. If we were to actually graph it out, what you would see is that the fast oscillations tend to die out really quickly, but the slow oscillations tend to take more time. So 3 Blue 1 Brown has an amazing video actually showing like what this would look like, but that's kind of a substitute for that. These are x, these are temperature. You start out with this, right? Eventually, like the really high oscillation stuff will kind of die off. So we'll end up with something more like this, and then this will also be decreasing, right? Until eventually it tends to 273 Kelvin. So yeah, that was Fourier that was like the Fourier analysis for this one problem. Shouldn't have taken as long. I was kind of like lazy about certain things, and I probably should have done a little bit more practice beforehand. So yeah, how long has the stream been going on? You know what? I'm gonna. Yeah. I think I'm gonna try out one more. I'm gonna try. Hydrogen would hydrogen be good? Hydrogen would be a little much, but I think I'm just gonna try basic Poisson's equation. Or actually, yeah, let's do Laplace's equation. Laplace's equation is pretty simple. And but I'll be doing it in spherical coordinates, so that'll make it a little bit more difficult. So yeah, if anyone wants it, this is the solution. Okay, so now I'm not gonna do let's see, what would be Laplace's equation is a bit simple. Is actually pretty simple compared to the heat equation, because it's just Laplace squared some potential 0. Poisson's equation is basically you just add a function in here. So this would be like this guy equals some f of function. Right. Okay. So now, the reason I want to do it in spherical coordinates is because there are actually a few more equations that are pretty useful. They're not just sines and cosines. Sines and cosines show up in one place, right? And that's one way to solve a differential equation. But there are actually a bunch of other polynomials. So in this case, if you do something in spherical coordinates, you tend to get what are known as the Legendre polynomials. So in this case, I actually have a reference for this one, so this should help. Yeah. So we're going to get a hollow conducting sphere of radius r sits in a charge-free region in an electric field. The surface of the sphere is at a fixed potential, dependent only on the azimuthal angle. So boundary condition. Yeah, there we go. Boundary conditions that. Do we write this? Yeah. Okay, sorry. I just need to get like my bearings. So real quick, we are going to solve this differential equation. Del squared phi equals 0 in spherical coordinates where potential and our boundary conditions of potential are theta equals some f theta, right? And there's nothing else. So the potential at this point, this is the only thing determining the potential. And we're going to try to find the potential inside and outside the sphere. Substitute the boundary conditions then. Okay. So that's kind of a brief refresher of spherical coordinates. So first thing, this is going to be the xy plane. So imagine you're looking head on, and this is going to be your point, right? So this is your theta, this is your r, and then if we go back, this is z. And if we go back to kind of more this view, right, where like the z is coming out of the page and you just can't see it, x, y, this is your phi, and this length here is r cosine. So really the only thing we need to know though is the Laplacian and spherical coordinates to get through it. And the other thing to note is that given this boundary condition, note that there's no phi dependence, or there's no phi dependence. There may be radial dependence, but there's no phi dependence, which means this is a solution in 2, where our solution will only have azimuthal dependence, so like this angle from the z-axis and the angle from the end distance away. So if you want to imagine, you can model, say, a dipole with this just by putting like a plus here, minus here, right? Or you can imagine a sphere where this potential is plus and this one's minus, and it's the same on the top as it is on the bottom. So either way will work. Anyway, moving on. Let's just jump into it. So, Laplacian and spherical coordinates is, so it's quite annoying to memorize. Yeah, so in this case, we're not going to write the full thing, but this expands out to one over r squared r squared d phi r plus 1 over r squared sine theta sine theta phi over theta. And then there's also a fourth term in there, or excuse me, there's another term in there for the full Laplacian, but we won't need it, and it'll go to 0 since our function won't depend on any of that. That's nonsense. I'll find it for reference though. No. Normally you just either look it up, or if you get high enough in math, you know enough about tensors to derive it. But yeah, so this is that guy. And let's just get started. This will be a little bit easier since I don't have to plug in as many numbers as less on. So in this case, we're going to assume that phi as I'm gonna call big R A. So this just means that at a fixed point at some constant radius, that the dependence is just some function, right? Some function of theta. There's none of this. It's more this like kind of thing. So how close you are to the top of the sphere versus how close you are to the bottom of the sphere. That's the only thing that matters at one specific radius. Real quick. Sorry. But yeah. So now we're going to assume that phi r theta is actually some function of this times this. Okay? And as you would expect, we plug this into the differential equation. And this looks a little bit messier, but this theta is going to come out here, and this big R is going to come out here. So they'll kind of get removed. So the first thing we do to make our life easier is we're going to multiply both sides of this equation by r squared, since they just have to be in the denominator. They don't really do anything. I'm going to have to follow this one. Oh, sorry if I keep going off camera. I'm just going to have to follow this one a lot more precisely than the other ones. Because this one's a bit harder. That one's just like, oh, look, we got sines and cosines. This one, I'm going to have to do a series solution to a differential equation, and then I'll have to set specific conditions on the coefficients, and it's just going to be a mess. Okay, so first thing, we just multiply by the r squared to get rid of that stuff. Next thing we do, I might skip a step just to make it easier on us. But yeah, so we multiply the r squared, and then I'm going to pull out the stuff. So what we get is theta times dODR. And this will actually turn into, oh man, I forgot this other. These will actually turn into just regular derivatives because we had that earlier. Because this is just a function of R. So, anyway, that gets rid of that guy. Cool. And we have 1 over sine theta, d over d theta. And this becomes the big. And I'll just add this here. RR equals 0. Okay, so we do the same trick as before. We divide by these guys, right? We end up with 1 over big R, d over dr, r squared d over r equals negative 1 over big theta theta sine theta d theta theta. So we get this, right? Now, the trick here is that this is going to end up equaling a constant. And once again, for finding the exact constant, you have to be a little careful. Or you don't have to be careful. It'll solve itself later. It's just more annoying if you don't. Yeah, I remember. Okay, so yeah, this constant ends up like you have to like kind of backwards. You have to know ahead of time something that'll make it nice, which you can get if you solve the differential equation. You plug it in, but the constant's going to end up turning out to be L times L plus 1. This is a really nice constant, but I think just lambda will work. Let's see here. Yeah, once again, you have to look a little bit ahead, and it'll turn out to be really nice. Well, so we got this, and I think, does the R take the negative? No, it does not. Okay. So yeah, I'm gonna keep the lambda, or I'm gonna keep the L over L plus 1 here. Once again, this isn't something you know ahead of time. This is something you do. You solve it, you get there, and then eventually you're like, huh, this would be nicer if this was L over L plus 1. So we're just gonna go with lambda for now. And we're gonna focus on solving this part here. This part turned into a little demon, but anyway. D over dr, r squared, r over d. This is gonna get annoying because I have to keep saying it as that, minus lambda big R. 0. We can do this with just product rule. This turns into r squared, t squared r dr squared, plus 2r. So this one we take the derivative, this times derivative of this. The other one we're going to do derivative of this times this. Right, so this becomes 2r dr minus lambda r equals 0. Okay, so now this one is a okay, I'm still on the right track. So now normally for differential equations you try to guess e to like some nx or some kx or whatever. In this case, if we take the derivative of this twice, right, we're gonna, like, if we do it with a polynomial, we leave this as is. We take the derivative of this, so we're going to guess r to the n. If we guess e to the x, this just won't work, or something like that. So we're going to guess, and I'll make the substitution now, here, just just because it's going to be nice later. I'm going to guess that this is r to the n, so it's just some kind of polynomial. Anyway, I'm going to take this guy, I'll plug it into these guys. I end up getting r squared times n minus 1. Yeah, you see these might be related. R to the n minus 2 plus 2r n times r minus 1, or excuse me, r to the n minus 1 minus L times L plus 1. R to the n. Alright, so once you get all this worked out, this times this gets r to the n, this gets r to the n, this gets r to the n. So you know, with r to the n times n minus 1, plus 2n minus L times L plus 1. Equals 0. Okay. Yeah, here's where it kicks in. So in this case, this is just a quadratic equation in terms of n. Yeah, so this becomes r to the n squared minus n minus L over L plus 1. Okay, and all you need to do is plug this into the quadratic equation. 0, remember this has to work for all r. So this term can be anything. You can't guarantee that's going to be 0, so we're just going to focus on this. And if you plug this guy in the quadratic equation, what you get is 1 plus or minus 1 minus negative, so this is plus 4 times 1, 4 L times L plus 1. This is all it does, right? Over 2. Okay, so this is what n could be. But now if we expand this guy out, this becomes 1 plus or minus square root of 4L squared plus 4L plus 1 all over 2, which this can factor out into 1 plus or minus square root of 2L plus 1, right, all over 2, squared. So then we can try and just cancel them out to get 2L plus 1, right? I'm sorry. Oh, okay, so this should be plus 1, because this n times this minus 1 plus 2n plus 1. So this becomes negative 1. Nothing else changes. This becomes negative 1. This becomes negative over 2. So this really kind of goes into two things. It could be either L or negative L plus 1, right? And it's kind of funny because, anyway. So this means our two solutions are basically solution of this part r, the function of r equals, and I'm going to call this L because this function of L equals C1 r to the L plus C2 r to negative L plus 1. Now, this is actually, you've actually seen this before. If we let L equal 0, right, so we let R 0, right, we get C1 plus C2 over R, right? And if I happen to plug some of these in, you might be able to recognize, like, if I just, for some reason, plug in C2 equals 1 over 4 pi epsilon naught Q times Q over R, this is the Coulomb potential, right? And then this guy is just a constant, because we can just add a constant anyway. So this one's kind of more fun, I guess. But yeah, you end up getting Coulomb's law out of this if you do it. And you don't even need to consider the angular stuff, because once again, Coulomb's law works without angular stuff. So anyway, this is our solution of RLs. I'm going to go ahead and erase. Let me erase the RLs for a second. So this is kind of the thought process and blah blah blah. Linear differential equation, you can do a linear combination of the two. L equals 0 is Coulomb's law. So now I'm just going to put this guy in a box over here. Now I'll actually have to. I'll just put it over here. That's not legible. Alright. I'll write it backwards. Okay. So erase this guy. And that's the R part, and that one's the easy part. But we can actually go a little bit more once we get to this part. This part, it's a similar situation. We don't know what L is. This will tell us what L is eventually, or give us restrictions on it. But anyway, and oh yeah, we need to plug in boundary conditions. Anyway, so we get this. We get 1 over sine theta sine theta big theta. Oh, sorry, I'm writing parentheses. Equals negative lambda L times L plus 1 theta. And I'll remove this because we know it's theta anyway. So that puts us there. We can move on to the next step. Yeah. Also, fun fact, this kind of L times L plus 1, if you square it and multiply by h bar in quantum mechanics, you end up getting the angular momenta. Or you get the angular momenta. So anyway, now we're going to do kind of a weird trick here. We're going to let mu equals cosine theta. So mu equals cosine theta, right? This would mean that d mu equals negative sine theta d theta, right? This would also mean that sine theta equals 1 minus mu squared. Take the square root of that. Okay. So now we can kind of pull a little sneaky trick here. I'm gonna rewrite this as sine theta or sine squared theta over sine theta. And if you notice, we're going to have negatives here. Like, this guy is here, and it's also over here. This sine squared theta is equal to 1 minus mu squared. So that goes up here. And since this is a function of theta, we can just rewrite in terms as a function of mu. So what that ends up doing is we end up getting, and this negative sign will cancel out. We get d over d mu times 1 minus mu squared. D, this is still the theta component. D mu equals negative L plus 1 big theta. But this time I'm gonna explicitly say it's a function. And this is known as the Legendre differential equation. So now what we're going to do is we're going to expand this out, take the derivative. Because the Legendre polynomials are written as a p instead of a theta, right? I'm actually going to do this. They're normally written simplified as p, so I'm going to just do p mu. Right, and the other thing is I'm just going to say theta. Right. If I want, I could go up here and indicate that. I might as well. Right, and mu is cosine theta, so eventually we're going to plug cosine theta back in. Or I could even write it like this. Okay. So moving on, if we take the derivative of this guy and expand it out, this becomes, well, this one's easiest, so we're going to do 1 minus squared. This becomes d squared p. I can write bigger. D mu squared. Right? And we take the derivative of this section, that gives us negative 2 mu. Leave this as it is. D. Bring this over here, plus L times L plus 1. Okay, this is known as the Legendre differential equation. And there's no closed form solution of it. So you can't write as like e to the x or like cosine or something like that, or even a polynomial. Well, you can't write any polynomials. So we're gonna try a series solution, and we can abuse a few facts. Since we're dealing with physics, there's a good chance that this is analytic, meaning that I can rewrite it in terms of a Taylor series. So I can write it as a series of polynomial, infinite, possibly infinite length. And well-behaved, analytic, they're kind of the same thing. So now I'm going to guess that p mu sum n equals 0 to infinity sum, what do I have in my hands? Let's just do a n u to the n. Right. That's just my guess. So it could turn into a it could turn into some kind of polynomial solution. It could do something weird. But I should be able to represent every function as this, even if it's not like a nice function or an analytic function or anything like that. Right. Anyway, so now all we gotta do is we gotta plug this in. First, I'm gonna write p mu sum 0 infinity u to the n, right? And then if I do p d, I take the second derivative of p I don't know if I'm standing in front too much. Second derivative p squared. This ends up becoming infinite n equals 0 n times n minus 1 an mu to the n minus 2. So all I did was just said it's some polynomial of some sort. I take the derivative, take the second derivative. Now I'm going to plug that back. All I really need to know is this equation. So I'm gonna write it over here and then kind of erase everything but the boundary conditions and this guy, because I've already done all the work here that I need to. So 1 minus mu squared p over mu squared is 2 mu plus L plus 1 it's not written too cleanly, but should work. And then I already know that p mu, I'm just going to assume it's an analytic polynomial of some sort. I just really need the space. I guess I can leave that up there since it's not doing anything. Anyway, so now we're just going to plug this in to this. We're going to get 1 minus mu squared. Remember, second derivative of this, sum n equals 0 to infinity of n times n minus 1 an due to the n minus 2. Right. Plus, minus 2 mu sum infinity n equals 0 n times an to the n minus 1. Okay, and then last term is just going to be plus L times L plus 1 sum infinity equals 0 an mu. And all this has to equal 0. Okay, so now I'm going to multiply this into here, right? And that'll end up giving mu to the n. I'm going to multiply this into here, and then I'm going to kind of break this up into a few things. So first off, let's just multiply the 1 out. This becomes infinity n equals 0. I don't need that. Well, I'll leave it up there just so I don't have to go back to anything. n minus 1 an n minus 2 minus sum infinity n equals 0 n times n minus 1 an. This mu squared goes into here, so we just get mu to the n minus 2. This mu goes into here, so we get 2 sum 0 to infinity n mu to the n plus L times L plus 1 sum. That was an abysmal sum. I'm glad that you probably couldn't see it. An mu to the n 0. Okay, so first off, notice that all these terms are summed from 0 to infinity of some constant times mu to the n, right? By the distributive property, we can combine them. So let's just do that. This one's a little weird because it's mu to the n minus 2, but we'll do a trick for that in a second. So n equals 0 and n minus 1 an mu to the n minus 2 minus, or let's do plus, and then I can do it from this way. So plus infinite sum n equals 0 of L times L plus 1. And all these are times an too, so that's nice. So it's an mu to the n. Minus 2n from this guy. Minus n times n minus 1 from this guy. all times an u to the n. Okay. So now this one's a problem because this has to equal 0. Okay. So I'm going to try to combine this into one sum, and I'm going to do a little trick, right? So the first term of this series, if we plug in n equals 0, we get 0. Second term, we plug in n equals 1, we get 0 because of this term. So the first two terms don't actually matter, right? So now I'm going to make the substitution n goes to n plus 2, right? So everywhere I see an n, I'm going to replace with an n plus 2. So, for example, n equals 0 plus 2. Yeah, and it won't change this. Change it from 0. Yeah, okay, I remember. So I'm going to replace every n with an n plus 2. So this guy, now it goes from n to negative 2, right? Because I need to account for those two terms. This becomes n plus 2. This becomes n plus 1, because it's minus 1. N plus 2. This becomes mu to the n. Now, why do we make this negative? Well, if I plug in negative 2, I get a0 times 0. Right? So I have to get the original thing back. So if I plug in negative 2, I get negative 2 here, I get a 0 here, I get a minus 1 here, and I get a 0 here. Right? And that's what I get if I plug in 0. If I plug in a 1, I get 1, 0, a1, u to the negative 1. Right? So if here I plug in 2. So this is 2. But now we can do one more thing. Because if we plug in 2, because if we plug in negative 2, we get 0, and if we plug in negative 1, we get 0, those terms don't contribute anything. So we can actually just replace this with just a 0. So it'd be like sum n equals 0. Sum. What's a good variable? Let's use k again. K equals 0 to the n. If I do k, well then this is 0 plus 1 plus 2 plus 3, all the way up to n, right? I don't need the 0 term in there. So if I want to, I could just rewrite this as k1, skip out the 0 term, right? So then I would start here, and I get the same exact. Now that we've gotten this format, notice that everything is in terms of a sum from 0 to infinity of mu to the n, right? So now I'm going to combine these two as is. So for now, this is mu to the n. I'm going to factor out the mu to the n and put it at the end. So this is plus L times L plus 1 an well, I'll still keep the an's together, minus 2n minus n minus 1. This might actually be a little harder. And all that times mu to the n, all that has to equal. Okay, so we got an expression, right? And we kind of always run into similar problems. If we plug in, we could plug in any value of mu into this, and it'll always give us something different. So if it equals, so this needs to be true for every single possible mu n. And the only way to do that is to assert that everything in here, every single coefficient has to be 0. But in this case, the coefficients are these guys, right? So now, if we take all these guys, and we have to set them equal to 0. So I'm going to erase this little substitution. So really we get n plus 2 times n plus 1, an plus 2, plus, I'm going to actually expand this out because this will be a little bit nicer. It's L times L plus 1 minus, this becomes minus n squared, this becomes plus n, so this becomes minus n squared minus n, which is minus n times n plus 1. A n equals 0. Make sure I got that right. Yeah, so this is correct. Okay, so now what's that get us? Well, if we take an and we plug it into, so now let's just try to get something useful. If we take an, and we want to solve for an plus 2 in terms of an, we get a plus 2 is equal to, I'll subtract this from both sides, and doing so will flip the sign, so these two will flip. So we get n times n plus 1 minus L times L plus 1 all over n plus 2 times n plus 1. Okay, so this actually looks maybe a little weird, but this is actually pretty good. We have kind of a second, we have a second order differential equation. This guy, right? And it's a second order linear differential equation, so we need solutions that are determined by two constants. In this case, we have our two constants, because if we do A0, we can get A2, A4, A8. We can get all the evens if we know A0. And if we have A1, we can get all the odd numbers, so we end up getting all the terms in the series. So this is correct in a sense. Now I just need to make sure I have the correct expression, because I always mess this part up. Yeah, no, this is correct. There's a trick we can do to factor this, and it's a little weird, but yeah. Oh, okay. So you see how this is like these two are kind of equivalent here. So L, N, L plus 1, N plus 1. Okay, so if we expand it out. Okay, so one way to think of this is if L equals N, this is 0. Right? So that means that this thing up here has to be divisible by L equals N. So, did I forget the minus sign? Hold on, let me check real quick. No, I did not. I already included it. So what this means is this has to be divisible by N. In this case, I believe it's N minus L would work. Yeah. So N minus L, right? And then if we kind of factor it out, we'll end up. This is just factoring. You could factor it any way. It doesn't actually matter. But we get L time. What would be the best way to write this? L plus N plus 1. I'm putting this in parentheses just for our sake. Because it makes it a little bit more concrete what's going on. All over N plus 2 times N plus 1. Huh. I'm surprised I got this far than it was. Oh, so I'm sorry. There's an A in here. Okay. So what this means is if we wanted to, we could represent our opponent. I'll keep this. I gotta put this somewhere. Yeah. I'll put it over here. So an plus 2 is equal to n minus L times L plus n plus 1 over n plus 2 plus 1. Yeah. Okay. So now I don't really need to go back through the kind of series stuff. I've already done that. Yeah, punchline's about to drop on this one, but I'm going to go back up. I'm going to erase all this. Yeah, I really only need this and to know that P is a polynomial in U, but it's not too hard to remember. Okay, and I do have references other places. If I erase something, I'd probably be able to fix it anyway. Okay. So now, this equation is pretty cool, but there's a bit of a problem. Well, let me actually write out the full polynomial here real quick. So, or not the full one, but EL for the function of mu would be equal to some A0 times 1, right? And then A2 is going to be, so it's going to be, we plug in 0 here, we get negative L times L plus 1, so minus L times L plus 1 all over n plus 2, or all over 2 times mu squared. Plus, same thing, now we're plugging in 2 for n, so this becomes, in this case, 2 minus L, wait, hold on. Yeah, okay. This becomes 2 minus L times L plus 3 over, we plug in 2 for n, so we get 4 times 3, which is 12, so 12, but it's times an, which is times L. I'm actually going to rewrite this like this. This would be correct, because the oh, because this was negative, right? That's what was throwing me off. So this is negative. That would have been what it was. So I'm actually gonna do this. This might be a little bit of a slight composition. Normally, I don't like having negative signs out front, but I think in this case, it's more clear it's gone. So this becomes L minus 2 times whatever this is. So L times L plus 1, and then we multiply by the 2 from earlier, so this becomes 24, right? So there's like a 2 in this part, there's a 2 from this part, and there's a 12 from this part, right? Times mu to the fourth. Minus, because it keeps flipping sign every time. So in this case, we're plugging n equals 4, so we get L minus 4 times L plus, 5 times L minus 2 from this guy, right? And then in the denominator we plugged in this case, so that was 0, that was 2, this is 4, so we end up getting 6 times 5, so that's 30 times 24. This becomes 720. Yeah, 720. Or if you want a little bit of a shorthand, but if you guess the pattern, it's this. And then this becomes 6 factorial, right? Okay, so then L minus 2 times L plus 3 times L plus 1. Right, mu to 6, and it just keeps going, right? So those are all the even terms. All the odd terms, on the other hand, look something like this. So for starters, A1 just has a mu on it, so we have a mu. In fact, all the odd terms will have a mu in them, so we're just gonna pull that mu out, right? This one doesn't. This one has a mu. This one has mu. That one has a mu. What the hell is that? 6. Anyway, but this one doesn't, so we can pull a mu out here. Anyway, so we plug in. In this case, we're gonna plug in. This is gonna be A1 times mu, A1 here. But now we're gonna want to find A3. So to find A3, we're gonna plug in 1 for n. So we end up getting, and it's going to be minus. It flips signs every time. This becomes 3 times 2. This is 3 factorial. It's going to continue in the same pattern as before. This become L minus 1 times L plus 2. Right? Times mu squared plus, and I'm not going to do the full thing as I did up here. So anyway, this will be 5 factorial once you plug in 3. Because we get 3 times 3 plus 2 is 5, 3 plus 1 is 4, 5 times 4 times whatever is the denominator of this is 3 factorial. It kind of works out. So we do L minus 3 times L plus 4 times L minus 1 is L plus 2. Okay. Fourth plus dot dot dot. And I believe it or not, I'm not trying to waste too much time with this kind of thing. Just like, this is the idea of what the polynomial would actually look like. Right? And you can see there's a general pattern. Maybe you can come up with a more succinct way of noting it than this. Or something that's easier to remember or something like that. But it doesn't matter. But now, we have a bit of a problem. This is supposed to be a little well behaved. But it actually isn't. If we just focus on this part, right, then the ratio between any two terms is going to be, we can do the ratio test and see if this converges. Every time you get a series solution, you have to check under which conditions does it converge, right? So in this case, we're going to check the convergence of this. So the ratio, we're also going to do it this term versus this term, so we're only focused on the evens or the odds. It doesn't matter, we'll use this. But so the absolute value of the ratio between an plus 2 and an is equal to negative L minus n times L plus n plus 1 all over n plus 2 times n plus 1. Right, times mu squared. That is the ratio between the two terms. So we can pull the mu square out. Here, because it's positive, obvious. And then we want to know limit as n goes to infinity. Goes to infinity. Okay, so sorry, there's a very slight inconsistency in my notes. Yeah, okay. Sorry, I'm just thinking for a second. Say pick any L, right? Because n is infinite, I could pick any L that's greater than this. So in this case, we're just going to say that n is significantly greater than L, right? So now, in that case, this whole guy becomes limit n goes to infinity of, and this is kind of like an approximation, so show an approximation symbol. So this becomes n squared over n, right? And n squared over n squared, right? Which is 1, or excuse me, which is approximately equal to mu squared. So this is kind of a nasty function. It basically diverges for, well, see what's weirding me out is I wrote down that it diverges, but I don't think it does if mu is less than 1. Or the absolute value of mu is less than 1. Which it would be in our case, but... Okay, so I see it. We need this to be valid for all our mu, and we need this to be valid for mu equals 1 at the very least. We might want more, but we want it to be valid for at least mu equals 1. So we have a bit of an issue, because if we let mu equal 1, then this diverges. It doesn't converge. So we can't actually use this. But there is one thing we could do. Notice that the ratio is fixed, but if at any point any an is 0, then all future an's are 0, or all future even an's are 0, and all future odd even are 0. So what we want to do is we want at some point in here for one of these terms to go to 0. And to do that, well, the only real way to do that up here is if L is an even integer, or an even positive and non-negative integer. So if L is 0, it stops here. If L is 2, it stops here. Right? So you get this one, but you don't get this one. If L is 4, you don't get this one, and you don't get anything further on. Right? But you can also do a negative. So if L is -1, you don't get this one. If L is -3, you don't get this one or any later ones. If L is 5, you don't get this one or any one later, right? So this one, remember how earlier we said, like, oh, we don't know what the constants are? Like when we saw the Fourier series, we didn't know what the constant was. That would actually get us a working solution. So in this, and then eventually we found that it had to be a like n pi over L, where L was an integer. In this case, we get the same thing, that L has to be an integer. So, let's see, new fact, L has to be in the integers. Okay, but that presents another problem for us. So, or that almost presents another problem. So let's say that we want this one, we want this to converge, so we say L is equal to 4, right? So we plug L into here, this gives us something, this gives us something, right? This one goes to 0 and all future terms go to 0. But if we look down here, there's no L minus 4 to cancel everything out. So that's one thing. The other thing we need to do is to say that we can only have one or the other, right? So we can only have evens, and so we can set this to equal 0, and then we don't have to worry about any of those. Or we can set this one equal to 0, and we don't have to worry about any of these. So moving on, we're going to say that A0 or A1 has to equal 0. So the product of them has to equal 0. That means at least one has to equal 0. So using those two facts, we can actually start working with these guys. And yeah. So if we choose an even integer, right? This will converge. This won't. So this A1 has to be 0. If we choose if we choose an even non-negative integer, so 0, 2, 4, 6, 8, we want to drop this, right? If we choose a negative odd integer, we also want to drop this. So non-negative even or negative odd, we want to drop this. On the other hand, if we have a a positive odd or a negative even, we want to drop this. Or drop this one, sorry. So what we end up getting are, and by the way, these are the Legrange polynomials for specific values of L. So, and there's also a convention, we have to normalize it, so it's a little bit nicer. But, yeah. Sorry, just thinking for a second. Okay, so let's do 0, and we can only choose the odds of the evens. Okay, moving on. I'm going to erase this guy. I'm going to leave that one up because I like the structure of that one. So yeah, and there are a few different ways of writing these guys. But yeah, there's also a convention that whatever Lagrange polynomial you choose, right, at plus or minus 1, it equals 1. So somehow all these terms cancel out. So you don't really normalize these, and then you introduce the constants later. So in this case, we could do P0 of mu is just 1. P1 of mu is just mu. P2 of mu is equal to, so now we plug in 2. We set this equal to 0. So this one gets us 1 minus. This 2 cancel with that 2. That gives us 3. 1 minus 3 mu squared. But we want it to equal 1. So we plug in 1 and we get negative 3. We plug in positive or negative 1. We end up getting negative 2. So we're actually going to do negative 1 half that. Or if you want, you could also write it as 1 half 3 mu squared minus 1. So that's the second Lagrange polynomial. And I'll do one more just for fun. P3, well, I need to give an example of this one. P3 mu is equal to, do it again, 1 minus, all these terms cancel, this is 0 up top. So this becomes 2 times 5 divided by 3 factorial, so that becomes 5/3 mu squared, and I'm going to throw a mu in front. So now, the only thing is, if we plug in 1 or negative 1, right, this guy equals, let me check this. I can just look at the normalization coefficient. Yeah. I think it's actually this rule. Or something like that, because this is obviously odd, so it'd go symmetric. I'll just say this. The absolute value has to be 1. That's the rule. Right? So now, what I'm going to do is I'm going to bring the mu in for a second. But, yeah, I'm actually going to add 2 rows. So this needs to be more like an absolute value. I wrote it lazy, but the absolute value of P negative 1, or here, I'll write this in the best possible way to make sense. So PL1 equals 1, and the absolute value of PL negative 1 equals 1. Okay, those are the two conditions. And the reason for that normalization is so that eventually when you end up multiplying by stuff or integrating over it, you end up not having to deal with anything. And it's pretty nice. So P3. And no chat. No. How much is the audio cutting out? Oh man, this would suck if like half the audio was cutting out. I wonder if it might just be a streaming thing, or if it's just recording. Worst case scenario, I can probably watch it back and then redo the steps and probably make fewer mistakes next time. Anyway, I'm gonna jump back to Twitch. So yeah, where was I? I'm just gonna keep going with this. So yeah, you get mu minus, once again, 5/3 mu cubed. But you plug in 1 here, you end up getting negative 2/3. That's not great, so you multiply that by 3/2, right? So you can do 3/2, or normally you would write it as 3 mu, or excuse me, something like negative 1/2, 5 mu cubed minus 3. Okay. So that's like the third Lagrange polynomial. Here's the second one. Here's the first one. Once these are all normalized, so you plug in 1, you get those two conditions. Anyway, moving on to the next step. There are other exploitable facts you can use, like if you want, you can get the normalization stuff for free. If you do, I'm pretty sure this normalizes them too, but you could do L plus 1, mu, 1 over L plus 1 times L plus 1 L L minus L yeah, so you can also use that fact to get the next one and it'll normalize everything for you. That's pretty great. So now we go through the whole thing, this whole process, right? And we end up with these Legendre polynomials, right? So big whoop, what can we do with them? How can we end up getting our original differential equation back? Well, or how can we use it to solve it? Well, just like the sines and cosines, the Legendre polynomials also follow an orthogonality relation. So it's P m mu n mu d mu equals 0. M does not equal n. N equals 1 over, or 2 over 2m plus 1. If m does equal n. So now we can do pretty much the same exact thing we did with Fourier analysis, but now we're doing it with a totally different function. In this case, the Legendre polynomials, they're orthogonal. So this means if we plug everything all together, we end up getting this guy times the Legendre polynomial. So our solution to this differential equation is to some infinity L equals 0 of C1, or I guess I could do, no, I used A up here. C1 r to the L plus C2 r to the negative L plus 1, right? That was way back earlier when we got this R thing, right? So we got this R thing here. We got this this PL from the theta term, right? So we get PL cosine theta, right? So that's just what we get from separation of variables. And then we can, yeah. you can actually get things like dipoles out of here. So like, if you do L equals 0, you get Coulomb's law, right? But if you do L equals 1, you end up getting the dipole equation, or the dipole potential. If you do L equals 2, you get a multipole equation, or they're called quadrupoles. So Coulomb's law is basically just, you just have a charge, right? Like you don't care, it's just kind of like just a charge in a general area, right? So this is L equals 0, this is L equals 1. This one, you kind of have a charge imbalance, right? So far away, this kind of looks like 0 charge, so it doesn't really matter. But this guy kind of looks like that. So L equals 0 is kind of like one charge area, is like kind of the average charge, total charge in some volume, right? L equals 1 kind of measures how spread out it is across a specific direction. L equals 2, that one's a little weirder, but it's kind of like something like this, right? And then L equals 3, it's just kind of like more and more stuff. Normally you go here, here, and then maybe here. Anyway. Oh wait, yeah, no, still going. I'm almost done now. I got through Lagrange polynomials. Legendre polynomials. Ugh. I'm calling them Lagrange polynomials. Right. Okay, so now let's actually try to do it for the original problem, which is just at some fixed potential, it's some function of theta. Right? So now, inside the sphere, we want our functions to be well behaved. And what that means is we can't have any singularities or anything weird. So we can't have this, right? We can't go to infinity anywhere. So what that means is I'm actually going to hold on. Sorry, I think I just got a message. Anyway, I'm gonna erase this line because, and then I want to rewrite. I'm gonna erase this guy, even though it's beautiful. I'm gonna have to move it, and this guy. Okay, and yeah, let's move this guy up here. So I'll leave that there just because it's there. Then we can do this. Now, do I have 0? Sorry, that should be theta. Fine. I can do it better. Fine. I'm all over the place. Sine theta. Okay. So that one's there. Your orthogonality relations, we're going to add them. A little box over here. Negative 1 to 1. You'll notice that negative 1 to 1 just happens to be the range of cosine, which is pretty nice. Mu equals. Oh, I can use the Dirac for the like delta. So remember, this is a lowercase delta, mn as subscripts, m and then n as subscripts, and this is 1 if they're the same and 0 otherwise. Imagine getting an entire symbol named after you for something like that, but that's what you get when you were born earlier. Kind of a trade-off. Okay. Erase these. And so now I'm not actually going to do the integral, not because like the actual thing, because it's pretty gross. How do I put it? Yeah. Because it's just basically you go in and you just calculate the integral, and that's it. That's like all you do. Right. Okay. So yeah. So now there were two implicit conditions. First off, that phi never goes to infinity. That's like the main one. And so now let's consider what happens if we let look inside the sphere, right? So if we look inside the sphere, let me just draw this out. This coordinate system doesn't actually matter as much, but let's say we have some r, right? This is just r in some direction. It doesn't matter for now. But if we go inside the sphere, right, r is the distance away from the center. At the center, we have r equals 0. So this term is fine. This term blows up, and it doesn't make any sense, and this whole thing's a mess. So what that means is all the C2 terms inside the sphere have to be 0. Likewise, if we go infinitely far away from this point, then these terms go to 0, which is good. But these terms actually become infinite. So we can't have those outside the sphere. So if we're gonna rewrite this in a more physical form, apparently my sound keeps cutting out. I was just now notified, so that's fun. Hope it works out. So what that means is I'm going to denote phi I for inside the sphere. R theta is equal to sum L equals 0, infinity. C1 REL. Well, I don't need that. EL cosine theta. Right. Then phi outside the sphere, so this is, I don't want to call it phi 0, but just make sure it's always round. Theta equals sum infinity L equals 0. C2 r to the negative L plus 1. EL cosine theta. Okay. So it'll change suddenly inside the sphere. And by the way, if you've ever done... it's getting darker, I should probably... If you've ever done physics 2, right, if you're inside a spherically symmetric charge, this PL term, remember that, like, P0 mu is just 1, and P1 mu is equal to just mu, right? Or actually, you just need to remember that P0 mu is equal to mu, and this is 1, right? If you've done Gauss's law inside a sphere of uniform charge density, right, you always end up getting that, oh, it goes up like this, so it goes up as some constant times r, call this k, so it goes up like kr, right? And then it decreases like a different constant, so like, I'm going to call this A, and I'm going to call this B overall, right? Well, remember, outside the sphere, here's a constant. If you plug in L equals 0, this term just becomes 1, so you end up with some constant divided by R, since L is 0. And inside the sphere, if you plug in L equals 0 and just 0 out everything else, you get some constant times... Yeah. Or you plug in L and L plus 1, I believe. Yeah. So you end up getting some constant plus this There's a weird cosine dependence in there. Let me make sure I have that right. Because that'd be pretty gross if I just didn't. Yeah, no, that's inside the sphere. And then outside the sphere, yeah. Oh, you can add a constant to that. Huh, weird. There's some, I don't know if there's a cosine dependency term. The outside sphere. Anyway, unless I'm doing something weird, PL should just be mu. But that means there's a cosine dependency inside there. Hold on. Thinking. Yeah, I don't know. But this pattern of like linearly increasing on the side of the sphere is this guy, and then decreasing 1 over inversely outside the sphere is this guy. So I better hurry up before it gets too dark, and then I'll just cut off the stream. So now, once again, we have f of theta, and we know that let's just do theta I for now. We go at big A, theta equals some f of theta, or I could do big R now because I've already moved past it where I used the big R earlier in the separation of variables. So we're just gonna do big R because that just makes more sense. Anyway, so I plug in big R into here. That equals sum infinity L equals 0, and I'm gonna do inside. So C1 big R to the L PL sine theta, right? So now if I multiply both sides of these by, I'm going to divide by R to the L, so I'll end up with yeah, that makes sense. So I'm going to multiply both sides by PM cosine theta. So in this case, I end up with, I'll deal with other stuff later. PM cosine theta equals sum infinity L equals 0, C L. You should have L's on them. They're not the same constant, they vary with L. So C 1L, right? C1L R to the L L cosine theta times PM cosine theta. Cool. So now we integrate both sides from, well, we could just make this substitution now, but mu is cosine theta. It's a U sub. I'm just trying to do it like early. Now, if we integrate both sides from -1 to 1, f theta E M mu equals, we do the integral, we switch the signs, everything cancels out except this, so this guy ends up becoming C1L R to the L times 2 over 2m plus 1. Once we integrate, because remember, everything else goes to 0 except for one term where L equals m. And when L equals m, we get this guy. And then these are constants, we just pull them out. Right? So what that means is that C1L is equal to 2m plus 1 over 2 times R to the L times 1 over R to the L. times the integral from negative 1 to 1 f theta p L. Oh, this should have d theta. Well, I'll just leave the cosine theta in there, and then this becomes cosine from negative 1 to 1 becomes oh, it's pi to 0. Pi to 0. PL cosine theta. Theta. Okay, cool. So, likewise, we do the same exact thing for this one, and then it is quite literally not different at all, except this time we have it r to the L plus 1 times it. So C2L equals 2m. Oh, sorry, this should be L. 2L plus 1 over 2 times r to the L plus 1, integral from 0 to pi f theta PL sine of theta theta. It's the same exact integral, just slightly improved. Or why did I say that? It's the same exact process. So A and B and yeah. So the full solution is I can just erase this because I have it here. So you know these coefficients. And it turns into phi I r theta equals sum L equals 0, infinity C1 L R. Oh, and by the way, even though L is an integer, we only include the positive ones because if we plug in negative L, we would have gotten like we have it already, and I don't think the negative L's really do. The negative L's are similar to the positive L's. There's not too much of a difference. It like here, like you can imagine, here are the negative L's and here are the positive L's. So anyway, this becomes inside the sphere r over big R, the L, P L cosine theta, times the integral from negative 1 to 1 of f, but as a function of mu. So replace every theta with arc cos mu, and then you'll be good. P L mu. Okay. So that should be inside the sphere. Oh, I'm missing a. There's a 2L. Rest. Oh, I can rewrite it. But okay. So it's 2L plus 1 over 2 times little r over big R. It's the L times PL cosine theta times the integral from negative 1 to 1 of f mu L. So that's inside the sphere, and outside the sphere it's pretty similar, except this becomes flipped essentially. 2L plus 1 over 2 times r over little r to the L plus 1 times PL cosine theta, integral from negative 1 to 1 f L. Right. And notice that these two are, so normally when you solve a differential equation, you have different regions of solutions. You have to check to make sure that these are equal at the different regions. So if you plug in big R equals R, this term becomes 1, this term becomes 1, and you have the same exact thing. So these are the solutions. And if you want to do an example, you would, let's see. I think we tried something like this. So F mu equals plus V naught minus V naught. No, that's too close. So, like, here's an example one. This basically means the top of the sphere has a constant potential and the bottom of the sphere has a constant potential, and they're negatives of each other. So this equals V0 minus V0, mu greater than 1, less than 1. And I don't know, mu greater than 0, mu less than 0. I don't really care what happens at the boundary, so I could just leave it undefined, or I could just say, I could do this. So yeah, in this case, let me see what. I wonder how Legendre functions work with square, because this is basically a square wave. So, and you just do this integral. So let's find the L equals 0 term, just for fun. The L equals 0 term is going to be, it's going to be 0. That's kind of like the average potential or something like that. But it's going to be 0 because if you look at this, this becomes -1 for, if I draw it out, this is what it looks like. So this area equals this area, so they cancel each other out, so that becomes 0. This doesn't add anything. If instead you go for something a little bit more, like if we look at L equals 1, we end up getting the absolute value, because it's a step function. It's like this square wave times so we end up getting V naught absolute value from mu is our integral, and we're integrating from a to 1 to 1. And I think that becomes, and this is for either, it doesn't matter because this term is the same in both. Mu, this is an even function, so it becomes 2, integral from 0 to 1. Mu. So this ends up becoming not squared 0. So yeah, let's try L equals 2. What was the L equals 2 one? Yeah. L equals 1 again. Yeah, it's blah blah blah. Yeah. So for the L equals 2 term, what will we end up getting? That's equals mu squared minus 1. Oh, okay. So here's the thing. All the even terms are 0. So like the problem is if you try to add, like, say, in this case at least. So this is our function. It looks something like this. If you try to add an even function, you'll end up adding some here that you shouldn't be. You'll end up adding the same to both. So it's like you're putting too much there. You need to add odd stuff over here plus odd stuff over here. Right? So you need to increase whatever you have here and decrease whatever you have here. But an even function increases on both sides or decreases on both sides, and that doesn't work. It would be like shifting the entire thing down, or like kind of like adding, I don't know, it'd be like curling the ends up, something like that, right? And that's not good. That's not diverging away from the function. So all the even terms will turn out to be 0. If you want, you can prove it, because this is basically I'll rewrite it in like a more compact form, but it's v naught absolute value of mu divided by mu. So in other words, it turns all the even functions on L functions even in this case, but it doesn't matter. So let's do L equals 3, and I think that's where I'll end it. So in this case, the L equals 3 polynomial, I might do L equals 5. Yeah, so the L equals 3 polynomial, so PL 3 mu is equal to 1/2 5 mu cubed minus 3, right? So now we plug that into here, and we end up with negative 1 to 1. We'll bring the 1/2 out, and we have a v naught out front as a constant. So then we end up getting absolute value of mu over mu. That's the kind of top half is positive, bottom half is negative. That's what this part is. Times 5 mu cubed minus 3 mu. Mu, this is an even function, so this right here, because you get an even function times this cancels out the oddness of this, so it ends up being v naught integral from 0 to 1 of 5 mu cubed minus 3 mu. This equals v naught times 5/4 minus 3/2 equals negative v naught over 4. So I'm doing this all mentally. I'm trying to go fast. L equals 3. Yeah. I'm not going to do the higher order terms. I'm just going to write it out. So our kind of if we want to expand this full thing out, yeah, v naught over 4 is correct. If we want to just write out the example in this case, it would be let's just do phi I r theta. Is this inside or outside? It doesn't matter. The only thing that changes is this. So yeah, and you can do different approximations to make it whatever you need it to be. Oh, the L equals 0 term shouldn't be to anything. So it's like, here's an example. This would be v naught 3/2. This is for outside. R over R times P1 sine theta minus 7/8. If you're wondering where all the numbers are coming from, remember we have to add this term into here. So plus whatever we got last time. So R over R cubed times 3 cosine theta oh, I'm getting the sign wrong. So this should be squared, or this should be the 4th outside the sphere. Remember, this is L plus 1. So, anyway, moving on, you have that guy, that's good. So, plus 11/16 r over little r to the 6 e5 cosine theta dot dot dot, right? And let's see what you can get out of this. It's over r to the 4th. So yeah, when r is really big, right, this clearly goes to 0 for outside the sphere. But at kind of like a first order approximation, say like, if you just look at the first term, then you get something that isn't really a dipole. But you get like the r theta is approximately equal to, or I'll say proportional to. Yeah, a little approximately. I don't know if that's a real symbol. Cosine theta over r squared. And it's not Coulomb's law, but it's more of a dipole field. So dipoles tend to have r squared potentials. And it would look like, as you might expect, here's our little sphere. Positive charge, negative charge, negative charge, negative charge, negative charge. And I'm going to draw that. That's like our sphere. But what the potential really looks like is something like, or the electric field will look something like this. So, if any of you guys are familiar with a magnet, magnets are always dipoles, so they always look like this, but this charge distribution is basically a dipole, so that's why it looks like this in this case. Sorry. I probably should have switched to a different marker. I have other markers, but as you can see, the general vibe is you go up and out and around, so like up and out. Yeah, and oh, hold on. Oh, this is actually, okay, weirdly enough, inside the sphere, it goes the other way. So, like inside this, so it like goes around to here, right? But it's always positive to negative. So it goes like this inside. So it goes from top to bottom, top's positive, bottom's negative. It still goes top to bottom outside, it just has to go around. Right, so that's what this field looks like. And yeah. I think that's it for the stream. I've run out of natural lighting, and so now I look probably like a serial killer of some sort. Yeah. I think I'm gonna end the stream there. I wonder, I don't really have anyone to raid. So oh yeah. That looks really glitchy. But I don't know. Yeah, I think I'll just end without raiding because I don't have anyone to raid. Alright, well. Bye then. Hope you got something out of this. I probably have to re-edit this down to something more usable because I made several mistakes that took like at least half an hour, maybe a whole hour, just like, oh, okay, that's what I was doing wrong. But, yeah.